Okay, Assalamualaikum and very good day to all of you. Today, we will go on our third Webex on JIF419 Material Science. So we will learn about the strength of material. So, what is strength of material? The strength of material actually a study of internal effect in terms of stress and strain that caused by external loads or force acting on a deformable body or structure, or it also known as mechanic of solids. It describes how solid material will deform or will change shape and how they will fail or break when force is applied. So it will determine the strength, the deformation, the stiffness, and stability. The strength is determined by stress at failure, while deformation is determined by strain. So when a sufficient load is applied to a metal or other material, it will cause the material to change shape, to deform. So this change in shape is called deformation. For stiffness is ability to resist deformation, which means that load is needed to cause a specific deformation, and it's determined by the stress-strain relationship, by the stress-strain curve. In stability, actually its ability to avoid rapidly growing deformation that caused by initial disturbance, like buckling. Okay. There are three major principles in which load may be applied. First is tension, compression, shear. However, in engineering, many loads are torsional rather than shears. So in tension testing, or also known as tensile testing, actually this is a fundamental material science test in which a sample is subjected to a controlled tension until failure. So the result from this test are commonly used to application like quality control and to predict how material will react under other type of forces. So by pulling on something, you will very quickly determine how the material will react to the forces that being applied in tension. So as the material is being pulled, you will find its strength along how much it will elongate or it will lengthen. So in a compression test, actually compression test is a test in which a material experience opposing force that push inwards upon the specimen from opposite side, or it could be crush or flatten. So a compressed sample is usually shortened in the direction of the applied force and expand in the direction of perpendicular to the force. A compression test is opposite to the tensile test. A compression test determines the behavior or response of a material while it experiences a compressive load. So in a shear test, this test is designed to apply stress to a test sample that experiences a sliding failure along a plane that is parallel to the force applied. So generally, shear forces cause one surface of a material to move in a direction and the other surface move in opposite direction, so that the material is stressed in a sliding motion. A shear test is different from tension and compression in that the force applied are parallel to these two contact surfaces, whereas in tension and compression, they are perpendicular to the contact surface. A shear test is to determine the shear strength, which is the maximum shear stress that the material can withstand before failure occurs. Only shears tend to change shape of a body without changing its volume. In torsional force actually produce rotational motion. So this test twists a material or a component to a specific degree with a specific force until the material fails in torsion. The twisting force of a torsion is applied to the test sample by anchoring one end so that it cannot move or rotate and applying a moment to the other end so that the sample is rotated about its axis. The rotating moment may also be applied to both ends, but the end must be rotated in opposite direction. This is a definition of stress and strain, where stress is force over area, where strain is elongation of material to its original length. Okay. When a force is transmitted through a body, the force tends to change its shape or deform. The way in which the body deforms depends on the type force applied to it. So generally, stress is force divided by area. In tension and compression, the test area is perpendicular to the force. In compression, the stress acts to shorten an object, while in tension, the stress acts to lengthen that object. These two, compression and tension, is also called the direct force or direct stress or normal stress. In shear or torsional test, parallel to a surface. So it can cause an object to slide over another, and it tends to deform originally rectangular object into parallelogram. Or the most general definition is that shear acts to change the angle of that object. So this is the formula. Tension or compression stress equal to, or sigma equal to force over the cross-sectional area, where the area is perpendicular to the force. In shear stress, or tau equal to force over area, where force is applied parallel to the area. The unit is in megapascal or in newtons per meter square. Yeah, or we can summarize it in this slide. Okay, common state of stress. The common example is in a sky lift. The simple tension we can see in the cable, where in a simple shear we can see in this drive shaft area. And for compression, the simple example is on the balance rope as well as the bridge. Okay, for strain. When loads are applied to a body, some deformation will occur, resulting to change in dimension. The strain can be defined as the amount of deformation of an object experienced compared to its original size or shape, or deformation per unit of the original length. In compression, longitudinal strain shorten the object, while in tension, it lengthens an object. In shear, the strain that change the angle of an object, and that cause the line to rotate. As strain is ratio of length, so it is dimensionless, no unit, and is measured in radian. Note that if the strain is positive, it shows an increase in dimension, and if negative, it shows a reduction in dimension. For tension or compression, stress is equal to this formula. This E is called epsilon, where in shear, the strain is described by this formula. Gamma equal to tan theta, where theta is a strain angle. Or we can summarize it in this slide, the formula. So remember that when it involves the force, it's referred to stress, and when it involves the displacement, it's referred to the strain. So these are some example. You can do it by your own. Make sure to do it first before you look at the answer. Okay, elastic deformation. All solid material deform when they are stressed. And as stress is increased, the deformation also increase. So elastic deformation is a temporary shape change that is self-reversing after force is removed, so that the object return to its original shape. Or we can simplify it as if a material returns to its original size or shape on the removal of load of force, and there is no permanent deformation occur, it is said to be elastic. So elastic materials always spring back into shape when released and obey the Hooke's law. According to Hooke's law, the extension of a spring X and the applied force F are related by the spring constant K. F equal to Kx. This is the law of a spring, which states that deformation is directly proportional to the force, or the deformation in which stress is directly proportional to the strain produced. Okay, this type of deformation involve a stretching of the bonds, but the atoms do not slip past each other. The Young modulus, or modulus of elasticity, is a measure of the material stiffness. So it tells how much something will stretch elastically when loaded. The E can be defined by this stress and strain diagram. Actually, it is the slope of the stress and strain curve. If F and X is referred to the direct stress and strain, then E equal to stress over strain. Higher E, higher the stiffness. Okay, the first portion of the graph will be a straight line. The slope is the elasticity, or the Young modulus. The stiffness, and its measure a stiffness of the material. The stiffness is different from different material and different size of the material. So in elastic deformation, it actually involves the stretching of the interatomic bonds and reversible deformation, where stress is equivalent to the strain. Initially, the atom is in this state, and when load is applied, bond is stretched. When load is removed or unload, the atom return to its original shape. It means that it's reversible, not permanent. Okay, this is some example for elastic deformation. So another elastic property of material is Poisson's ratio. So in here, when you strain a body along one axis, it will change shape along the other axis. For example, this rectangular body. If it is in tension, its cross-sectional area A will become reduced. So if material subject to tension, it will shrink laterally. Those who subject to compression will bulk. So the ratio of the lateral and axial strain or longitudinal strain is called the portion ratio. Portion ratio defines how much strain occur in the lateral direction when strain in the longitudinal direction, in the Z direction. Note that, remember that nu is dimensionless. Theoretically, portion ratio for isotropic material is 0.25, and the maximum value or the value for which there is no net volume change is 0.50. For many metals and alloys, value of portion ratio is in the range of 0.24 until 0.30. Okay, another elastic property is shear modulus. In shear stress to shear strain can be represented by this formula, tau equal to G gamma, where gamma is the shear strain. Actually, G is shear modulus and also the slope of the linear elastic region of the shear stress strain curve. The elastic modulus, shear modulus, and portion ratio are related by this formula. P equal to 2G 1 plus mu. The unit is in Newton per meter square. This is some properties of material. This for metal. For Young properties of Young modulus, shear modulus, portion ratio, yield stress, and elongation. Okay, for plastic deformation. Plastic deformation is when the stress is sufficient to permanently deform the metal. So it's called plastic deformation. Characteristic of plastic deformation: stress not proportional to strain, and breaking and reforming of new bonds when deformation occurs. And it's non-reversible and permanent damage. For crystal, plastic deformation occur via slip and dislocation motion, while for amorphous or non-crystallized, plastic deformation occur via viscous flow. So in plastic deformation, initially the atom is in this state. When force is applied, the bond will stretch and plane shear. And after the force is removed or unload, the plane still shear. So the plastic means permanent deformation. As you can see at this area, this start the plastic deformation. Begins at this point. This point is called the yield point or the proportional limit, where strain divides from being proportional to stress. The phenomenon of yielding occur at the onset of plastic or permanent deformation. So this point of yielding is determined as the initial departure from linearity of the stress-strain curve. The position of this point, the point P, is difficult to measure. So to overcome this, a straight line is constructed parallel to the elastic portion of the curve at some specific strain offset, usually at 0.002. This is called 0.002 strain offset technique. So the yield strength is given by the intersection of this line and the stress-strain curve as it's bent over in the plastic region. This is the yield strength, intersection of the parallel line of 0.002 strain offset technique. Okay, for tensile properties, for low carbon steel, the stress-strain curve include both upper and lower yield point. The yield strength is defined as the average stress at the lower point. At this area, the yield strength is the average stress at the lower yield point. So after yielding, the stress necessary to continue plastic deformation until it increases to a maximum point M and decrease to eventual fracture, which is the F point. So the tensile strength is the stress at the maximum of the stress-strain curve. It happens if the stress is applied and maintained, then fracture will happen. However, at this maximum stress, net begin to form at some point called necking, and fracture ultimately occur at the net at this point. Yield strength usually more important than tensile strength. Once yield strength has been passed, structure has deformed beyond acceptable limits. If stress maintained, specimen will break. Okay. For ductility. Ductility is ability of a material to be permanently deformed without breaking when the applied load is removed, or deformation at fracture. Actually, it's measure of the degree to which a material plastically deformed by the time fracture occurs. The ductility can be expressed as a percent elongation or a percent reduction in area. The percent elongation is the percentage of plastic strain at fracture, where F is the length of the fracture. In percent reduction in area, AF equal to section area of fracture. From the graph, brittle is a metal that experiences very little or no plastic deformation upon fracture. Or we can call it a property applicable to a material if fracture occurs soon after the elastic limit is passed. While ductile, property applicable to a material if a large amount of plastic deformation take place between the elastic limit and the fracture point. Elastic limit is in this area. Brittle material normally comprise as iron, glass, and stone, while ductile material example is steel or some of alloys. Ductile materials deform much more than brittle material. Brittle material fails suddenly, usually with no prior indication that collapse is imminent. On the other hand, ductile materials such as steel normally undergo a substantial deformation called yielding before falling. Thus, it provides a warning that overloading exists. So these are mechanical properties of metals. Some mechanical properties of metals: yield strength, tensile strength, and ductility. Yield strength and tensile strength vary with thermal and mechanical treatment, impurity level, and others. While yield strength and tensile strength, yield and tensile strength and modulus of elasticity decrease with increasing temperature. The ductility increase with temperature. Why ductility increase with temperature? Okay, for toughness, this toughness is the ability to absorb energy up to fracture. Okay, it's actually the area under the strain/curve up to fracture. Material resistant, or also can be called by material resistant to fracture when a crack is present. It's the unit is the energy per unit volume, joule per meters power of 3. Ductile metals are normally tougher than brittle metals. As you can see in the curve, even though the brittle metal has higher yield and tensile strength, however, it has a lower toughness due to the smaller area under the curve compared to the ductile area. So that's why ductile normally tougher than brittle metal. So these some examples of material: smaller toughness like ceramic, larger toughness like metals and polymers, or smaller toughness is unreinforced polymer. So hardness. Hardness is resistant to permanently indenting the surface. Larger hardness means resistant to plastic deformation or cracking in compression. Actually, it's better wear properties. There's some material from lower to increasing hardness. From plastic has a lower hardness and diamond has a larger hardness. Smaller indents mean larger hardness. Hardness can be tested by Rockwell hardness test, Brinell hardness test, and micro-indentation hardness test. The Rockwell hardness is the most common test. In this test, various indenters are forced into the material surface, and it based on a different indentation depth. In Brinell hardness, hard spherical indenters force into the material surface, and it determines the indentation size. So in Rockwell, various indenter. In Brinell, spherical indenter. Rockwell, based on indentation depth. In Brinell, it based on the indentation size. In micro-indentation test, the test involves Knoop and Beaker test. In here, a pyramidal shaped indenter is forced into the material surface. So it less force than Rockwell and Brinell. Normally it's used to measure the brittle material like ceramic. So in micro-indentation, pyramidal shape is used. In Brinell, spherical. In Rockwell, various shape of indenters. This is the graph of relationship between tensile strength and hardness for steel, brass, and iron. As you can see that the hardness is proportional to tensile strength. This proportionality constant depends on the material. Okay, hardening. An increase in yield strength due to plastic deformation. The characteristic of this strain hardening It is the hardening in the material as they undergo plastic deformation. Materials become stronger during strain hardening due to the creation of dislocation. Higher strain hardening represent the higher ductility. When tough materials are used, design stress is taken as calculated stress level multiplied by design factor. Design stress is the design uncertainty, means that we do not push the limit. The safe stress or working stress QW is used based on the yield strength of the material. For ductile material, working stress is dependent on yield strength and factor of safety, and just as in steel and alloy. In engineering design, the yield strength is the important parameter. Where the factor of safety must be larger than 1. And make sure that QD less than QY for safe or for working stress. Okay, this is some example for design or safety factor. Design uncertainties means that we do not push the limits. Okay, factor of safety N. Normally between 1.2 and 4. So this is the design safety factor is important in engineering design. Okay, I think that's all for our third Webex session. And unfortunately, some of you didn't submit the quiz 1 for me. The due date is already finished. Actually, the due date is on October, if I'm not mistaken. So please make sure to submit your assignment as the due date given. Okay, that's all. Thank you.